You're listening to AI Podcasts. I'm Ethan, and today we're unpacking an ICLR 2025 poster titled Agent Skill Acquisition for Large Language Models via CycleQD. Quick takeaway first. CycleQD is an evolutionary, quality diversity approach that fuses specialist models and rotates focus across tasks. On Llama 3.8b Instruct, it beats standard fine-tuning and simple merging across coding, operating system, and database tasks, lands in the neighborhood of GPT 3.5 Turbo on average, keeps general language ability steady, and even transfers to an image segmentation setting.
That's a clear headline. Who's leading the work?
It's led by Kuroki at Sakana AI, with Taishi Nakamura, Takuya Akiba, and Yujin Tang. We'll say Kuroki and team at Sakana AI.
All right, before the how, what problem are they trying to solve?
Two persistent headaches in post-training agent skills. First, mixing data across skills like code, shell, and CQL requires delicate ratio tuning that's easy to get wrong. Second, the usual objective, next token prediction, isn't aligned with the metrics we actually care about, like pass at 1 for coding or success rate on OS and DB tasks. Reinforcement learning can help but brings reward balancing and engineering overhead. The question is, can we improve agent skills without hand-tuning data mixes or building a heavy RL pipeline?
So they're looking for a simpler path that still optimizes the real task scores. What's the idea behind CycleQD?
They adapt a quality diversity framework. Imagine a population of candidate models living in an archive. CycleQD alternates which task is the main quality objective each generation, coding, then OS, then DB, while the other tasks act as behavior characteristics that structure the archive. That cycling keeps progress balanced. The evolutionary operators are tuned for LLMs. Crossover is model merging in parameter space, and mutation nudges weights along directions given by singular value decomposition rather than just adding random noise.
Right, so the system doesn't just average experts, it explores beyond them. How did they set up the experiments?
They start from Llama 3.8b Instruct and build 3 experts, one for coding, one for database, and one for operating system tasks. Coding uses MBPP Plus from Eval Plus, while OS and DB come from Agent Bench. Metrics match the tasks, pass at 1 for coding, success rates for OS and DB. For compute reasons, they drop OS items that none of the reference models can solve. Archives are discretized by performance ranges, and they run a population over many generations with elite sampling for parents. Baselines include single-task fine-tunes, a simple multitask fine-tune on all data, and several learned model merging approaches.
Got it. And what happens when CycleQD meets those baselines?
CycleQD delivers the strongest average across the 3 skills among the 8 billion parameter baselines. It tops coding and OS with a mild trade-off on DB compared to the DB specialist, and overall comes close to GPT 3.5 Turbo on the combined score. Crucially, when they check general language ability, reasoning, math word problems, reading comprehension, common sense, the fused model stays near the base model, while a pure coding expert shows clear forgetting outside its niche.
That balance is the appealing part. Do they explain why it beats plain merging?
Yes, simple merging tends to stay inside the convex region spanned by the parent experts. The SVD-based mutation lets the search step outside that region without drifting into overfitting, and the cyclic archives keep diverse candidates alive long enough to improve. Their ablations back this up, cycling the target, using SVD rather than random noise, and sampling elites all contribute to the final gains.
You mentioned it transfers to vision. What did they test there?
They merge segment anything experts specialize for different segmentation niches, like camouflaged objects, polyps, skin lesions, and leaves. The best merged models retain most of the expert performance, and there's a clear pattern. The more similar the experts, the better the merge. That echoes the idea that compatibility among experts matters.
Makes sense. Let's put on the skeptic hat. What should listeners watch for?
Scope first. The core results are 3 computer science agent tasks. That's meaningful, but not the full agent universe like web navigation or robotics. Second, dropping unsolved OS items is practical, but it can shift difficulty. Third, success depends on expert compatibility. If experts are too far apart, merging may underperform. And while they compare against strong fine-tunes in several merging optimizers, they don't run head-to-head against modern RL-style multitask recipes. Compute details are outlined, and there's public code, though a full cost breakdown would help replication planning.
All right, if I'm a practitioner, what's the actionable takeaway?
If you already fine-tune small experts, consider a cyclic, population-based pipeline instead of hand-tuned data mixtures or a full RL stack. Start with your best single-task experts, use parameter space merging for crossover, add SVD-based mutations, and evaluate on the true task metrics. The recipe shows you can lift multi-skill performance while keeping language ability intact, and the same framework can extend to other modalities.
Nice. Could you wrap us up with a crisp summary?
CycleQD rotates which task it optimizes, merges specialists in weight space, mutates along SVD directions, and, on the reported benchmarks, beats standard fine-tuning and common merging strategies at the 8B scale, with language skills preserved and encouraging signs and vision. That's the story from Kuroki and team at OpenAI.
Thanks, Ethan. And thanks to everyone listening. This has been AI Podcast. See you next time.